And I just wanted to say a quick note about interconnection networks. If you guys get interested in interconnection networks as we go along, I highly recommend this book. I have not assigned anything from this book for this class, but this is Bill Daly's and Brian Towles' Interconnection Networks book. It's quite good. It's kind of the definitive guide on the subject matter. OK, so interconnection networks. We talked about buses, and we talked about memory protocols about buses. That's only one way to share information. Now, people may argue that's an intuitive way to share information because we had the ability to do loads and stores from our processor. But there are other ways to share information. So in today's lecture, we're going to talk about two main topics. One, how to share information in a different way, which commingles the movement of data with a synchronization primitive. We're going to call that messaging, which is in contrast to memory, or communicating via memory addresses. We're also going to talk about different ways to connect together processors, which can either have better performance or better scalability, i.e. have more nodes in the system. And OK, so let's compare and contrast buses to other forms of network and see why we might want to change. So this is going back to what we had just talked about. Let's say you have two cores on a bus. And let's forget about how you want to communicate. It could either be via shared memory, or it could be via messaging, or it could be via some other protocol, Ethernet, whatever you want to put here, which is basically a form of messaging. We have one core and wants to communicate with another core. Note, I don't draw any caches here, because there may not be caches, there may be caches. It's kind of immaterial here. And if one person wants to talk to another person, they can just yell at the other person. It's two people, so it's pretty easy to do. Now there is some challenges. We can't both talk at the same time. We might not be able to understand each other. So there's some arbitration that needs to happen. But in general, that arbitration is pretty simple. Only two cores or two entities on this bus. OK, now we go to more cores. So we have 4 people in a room trying to shout to each other. Well, or 4 people on a bus trying to shout to each other. And as we just talked about, the bandwidth can be a challenge here. The arbitration for the bus can be a challenge. And because we're talking about interconnection networks, the wire delay and capacitance of the network can be worse, or it could be a challenge here. So if we think about one core, and it needs to drive this shared multi-drop bus, there's a lot of capacitance on this bus. Much more so than this case. Because all of a sudden, we've doubled the length of the bus, so the wires are longer. And we've also put more loads on the bus. So there's actually more capacitance on this bus. OK, now we start to think about trying to build a bus that has a lot more cores, in this case, 12. And if you're this core, you have to go shout to that core. There's no pipelines around on this bus or anything. You go to shout, and it has to propagate all the way down here. And we're talking about high rates of communication. You actually have to wait for the time of flight of light from here to get down to there. And because if you're using something, let's say, like a Snoopy protocol or a broadcast protocol, because that's all we have here, we have to wait for any node here to communicate with every other node. So we have to wait for the worst case time for this node to communicate to that node every clock cycle. OK. And as I said, there's capacitance. So it's not quite just a transmission line. So it's not just a transmission line problem here. We also have to worry about the capacitance in trying to drive all of these different receivers. And it's a multi-directional bus, so we have to have effectively tri-states and the ability to drive or just receive. Well, all of a sudden, we have 12 people. And actually, we have 12 people in this room. So let's all try to pick a number between 1 and 10 and shout it real fast on the count of 3. 1, 2, 3, 5. OK, I shouted 5. I don't know what everyone else said. So that's, could everyone hear everyone else's? Does everyone know exactly what all other 10 people said at the same time? Or 12 people said at the same time? You heard your nearest neighbor, OK. But did you know what Yanji said? No. OK, so this is a challenge. And if we need to guarantee that only one person can yell on the bus at a time, we need some arbitration. But the arbitration logic is slower now because we have lots of people communicating. So we have to run a wire from this node down to this node and then have it come back. And the arbitration logic, let's say over here, needs to make some decision. And the decision is slower because it has more layers of logic, more combinational logic, we'll say, to make an arbitration decision. OK, now if we go to 1,000 processors or 1,000 cores on a bus, we couldn't even have 12 people in a room shout at the same time. You can't have 1,000 people in the room shout at the same time. And physically, the distance of the wiring between these 1,000 different nodes is going to decrease the speed of this bus significantly. So this is something to think about. So this motivates us to take these same 12 cores and think about some other way to connect them. Now, what I'm going to show here is what's known as a switched interconnect, or sometimes known as a point-to-point link solution. Now, point-to-point does not mean that this core can communicate directly with every other core. That has a different name. We'll talk about that later today. Instead, point-to-point just means each link only has one sender and one receiver. And then you use switches along the way to make decisions and to route. So if we look at this, we can actually have multiple nearest neighbor communication happening. So all of a sudden, by adding this switching, we can both have connectivity between all the different nodes, but we can also have sort of sub-conversations happening. But this still allows for this processor here to go communicate with the one that's at the farthest extent. And we need to decide how to do that, whether it communicates sort of this way, or that way, or some other squiggly line. We can also take the same point-to-point switch interconnect network, and like a bus, which we can increase the width of the bus, which does not help us with the occupancy on the bus, we can add more networks, or we can effectively add multiple concurrent switched interconnection networks, or we can increase the bandwidth on these buses. So it's similar sorts of ideas there and similar sorts of bandwidth tricks you can do to increase the bandwidth on buses. You can play on switched interconnection networks. OK, so this is just a very broad overview. Now we're going to get into some more specific ideas.